Hello, and welcome to my first video in a series that I'll be calling Simple Physics, where we'll try to make sense of some harder physics concepts. However, today we'll start at the start, that being with rectilinear kinematics. Rectilinear meaning straight line motion, and kinematics meaning the study of motion. This will be the very first concept of physics, dealing with some very simple objects moving in a straight line path and trying to make sense of them. Start out with this, let's define some concepts. Of course, you must know about the concept of vectors and non-vector components. A scalar is something with only either a direction or a magnitude, whereas a vector is something with both direction and magnitude. An example of a vector would be the train is moving 5 miles per hour east. Now let's get into what this has to do with here. Starting with, the very first concept is of either the non-vector component distance or the vector component displacement. Now displacement is, say an object, let's say a car, starts here at say x is equal to 0, or let's say this is our origin. And let's say it moves 10 meters this way. We'd say for displacement, now for distance, we'll say it moved 10 meters. For displacement, we'll say it moved 10 meters to the right. Next one, speed. The speed, say it moved this way at some certain speed. Let's say this happened in 1 second. We'll say this one happened in 10 meters per second. Now the vector component is velocity. We'll say it moved 10 meters per second to the right. And finally, acceleration. Acceleration is inherently a vector quantity. Now let's say it moved 10 meters per second for a total of 2 seconds, which will give you 5 meters per second squared, which is the acceleration. The displacement is how much it moved, the speed is the rate at which it moved, and the acceleration is the rate at which the speed changed over time. Now let's give you some examples so we can get into that. With kinematics, one of the main assumptions that we like to make, and one thing with the great four equations of rectilinear kinematics, is when we have an acceleration that is constant. Now it doesn't mean it's zero, it just means that it is constant. Meaning the velocity and displacement can change, but the acceleration cannot. Here are the four main ones. We have v, which is the final velocity, is equal to the initial velocity, plus acceleration times some due time. We have displacement is equal to this here, initial plus final over 2 times time, the average of these 2 times time. Displacement is equal to v naught, the initial speed times t plus 1/2 at squared, and then v squared, which is vf squared, is equal to the initial velocity squared plus 2ax. First off, we'll be starting in one dimension, then we'll move on to some applications in two. Although you can do 3 dimensions of kinematics, they aren't as much well required, and as one professor once told me, we can sometimes move our frame of reference so we don't have to worry about those. I'll start with one example. Let's take a boat. The boat's in the water, and it's moving from here to here. It starts off at a speed. It's heading east at a speed of 5 meters per second. And it goes over to here where it stops 10 meters away. Let's start off with our knowns. One of the first things in any physics problem is to write down what you know so you can attempt from there. We know that our initial velocity is 5 meters per second. We know our final velocity is 0 meters per second as it stopped, and that the displacement, or the change in position, is 10 meters. Let's use our equations and try and see what we're looking for, because inherently what we're looking for is the time it took to stop. One other thing we can look for is the acceleration. What equations can we use to find these? Well, right now we have v, v naught, and delta x. Now it depends on what we're looking for. This one we cannot use because we don't have a or t. We're looking for one, but we can't look for both. This one here we could use if we're looking for t. Let us use this one here, v squared is equal to v naught squared plus 2ax. Let's solve for a in this equation. So we have 0 meters per second squared is equal to 5 meters per second squared plus 2a times 10 meters. This is 25, so we have negative 25 meters per second is equal to 20, in this case, meters times acceleration. And now we'll end up with negative 5 over 4 meters per second squared is equal to the acceleration. Now let's do a little bit of a litmus test. Does that negative make sense? What we'll be able to say is yes, because it's slowing down. It starts here and it slows down to 0. Thus, we're able to say that yes, the acceleration is equal to negative 1.25 meters per second squared, and that negative is indicating that it is slowing down. Now let's find the time, and I'm going to say we use that first equation. Vf is equal to v naught plus at to find the time. V is equal to 0, thus we know that our velocity of positive 5 meters per second. Move it on this side so it becomes negative, is equal to the acceleration times the time. We have two negatives here because we move this one to the left. Once the negatives cancel, we'll come up with a positive t, which is something we most definitely want. Divide this on both sides. We end up with 4 seconds is equal to t. So it stopped in the matter of 4 seconds. Thus we have acceleration and the time. Now this is an example of one-dimensional. Let's move on to a two-dimensional, onto one of our favorites, that being of projectile motion. Say we have a cliff, and we have something being rolled off the edge, say a ball. Now it starts at a horizontal. Now we're going to look at components for x and y. Now before we do anything, what do we know? We know that we're going to be neglecting air resistance. Because of that, we're going to start off in the x with a given initial velocity, let's say 10 meters per second. Now the final is also going to be 10 meters per second because there's no acceleration in the x, because there is no air resistance. As for the y, it starts off at 0 meters per second in the y. Now the final is something we're going to have to solve for. As for displacement, those are also solves we can look for. As for acceleration, it's 0 meters per second squared in the x, and it's fixed in the y at negative 9.81 meters per second squared, or negative 32.2 feet per second squared, and that's the gravitational constant as we know it. Now we can start solving for some certain things. Let's say we know this height here is 50 meters. Now let's try and solve for what we can. Now we know some things in the x and the y. Let's find out how long it takes, or in this case, how far it goes in the x. One thing to note from here is that there are some things in common between x and y, that mainly being time. Time is the same between x and y. From what we know here, let's start off and see what we can find. Now in the y, what we have is an initial velocity, an acceleration, and a height. What we can actually find here is possibly without time, v squared is equal to v naught squared plus 2ax. We can find out, now since we know the distance, the velocity, we can find the final velocity this way. So we have v squared is equal to v naught squared, which is 0, plus 2, with this case is g, negative 9.81 meters per second squared, times x, which is 50 meters. Once we plug in our numbers, we can tell that the final velocity is equal to the square root of 2 times 9.81 meters per second squared times 50 meters, which gives us 981 meters squared per second squared. Take the square root, we get 31.32 meters per second acting downwards. On to the next one, velocity is equal to, then we can plug this into this equation to find some value t. We know that time isn't a vector quantity, and thus it is present in both x and y. So we'll find here that the total time when this velocity is reached is equal to that final velocity divided by g. These are both negative, thus giving you a positive value for time, which is always correct. Always make sure your time is positive. You get some value of t, which in this case is 3.2 seconds, or 3.19. Now let's plug it into this equation using the x. So the total distance in x will be equal to v naught plus v over 2 times t. This will give you 20 meters per second over 2, which is 10 times 3.19, gives you 31.9 meters in the x. One final thing, if you want to look at the graphs, which is almost certain in all of these for projectile motion, is you'll see in the y, say it starts off at some value 90 and starts moving downwards parabolic. That's your x value. Now if we look at the velocity, it'll move downwards like this. And then finally, with acceleration, it'll stay like this. One thing you will note is that these are slopes of each other. That's something you'll get into within the calculus physics, but it's one interesting trend to note with all projectile motion problems. If you have to draw a graph, it'll most likely look at that if you draw the curve. Thank you for watching. This has been the first video on this subject. Next up, I will go into a little bit more in kinematics and then on to forces.